Here I give an explicit formula for calculating the critical t-value, which enables us as statisticians to dispense with the t-value table. This method improves upon my previous method, which utilized Dominici expansion. In fact, this method is equivalent to my previous method, but this method has the added advantage that it utilizes a reversion of series and calculates the critical t-value in terms of partial Bell polynomials, which can be computed efficiently. Here I show that the critical t-value with confidence interval ADA and degrees of freedom V can be represented as this square root function. The bulk of the computation actually comes down to resolving this U term, which I calculated in a previous video, but here I calculate using this partial Bell polynomial method. The computation itself really comes down to calculating these coefficients, which I denote as G sub n. And one thing that's positive about these coefficients is that when n is even, these G of n terms are equal to 0. And we actually found that also with the Dominici expansion. Here I show what each of these terms is equal to as explicitly as I can. This gamma term, which the expansion is expanded, the expansion expands. These gamma terms are just a product of this beta function multiplying 1 minus 2 times ADA, which is related to the confidence interval. And we showed this last time. This beta function is just a product of gamma functions divided by the gamma function whose argument is the sum of the two terms of the beta function. And inside this beta function, you have v divided by 2 as one of the terms, and then 1/2 as the other term. Recalling from the previous videos, it was important to make a note of this a term in the integral, this a term simply being v divided by 2 minus 1. So moving on to the coefficients, computing the coefficients, these g of n terms, it's explicitly given that these g of n terms are just going to be a sum in terms of these Bell polynomial, these partial Bell polynomials. And in these partial Bell polynomials, you have these f terms, which I also give an explicit formula for. You can calculate as many of them as you need. It's also important to note some notation here. I show that I'm just showing that this a to the k with a bar under it is the falling factorial, and this n to the k with a bar over it is the rising factorial. These partial Bell polynomials are great in the sense that they can be computed efficiently, and they can be computed efficiently via recurrence relation, and you can take that from Wikipedia. What's also interesting is these particular partial Bell polynomials, because every other term is 0, you only have to take them when I is odd and when n plus 1 is even. And another thing that's nice about these is that, and this is true for partial Bell polynomials in general, that bn1 is just going to give you the x of n term. And I show that each of these x sub n terms sort of relates to the position in which you find them in the partial Bell polynomial. So just some reference from Wikipedia. They give you a nice table which corresponds to how I've represented the x sub n terms. And they also give you a recurrence relation that enables you to calculate these partial Bell polynomials efficiently. Anyway, so that's basically the entire setup you need to calculate the critical t-value, I calculated this out for 4 terms. You can immediately see that these polynomials which appear as coefficients correspond to what we got with the Dominici expansion. And in fact, I put up a sequence on the online encyclopedia for integer sequences, A320842, which gives some interesting information connection to these sequences. But here I give an explicit formula for calculating as many of these terms as you want. And then just to make it more concrete, and then as sort of a final thing, I just show that this connection exists between these coefficients in the sense that these two methods are identical. One utilizes the Dominici expansion, and then this one utilizes reversion of series. I do need to make one correction, that in the Dominici expansion, to make it equivalent, you actually want to substitute negative a for a, and then these two methods are equivalent, and you get the correct answers, which correspond to the terms you expect to see in a t-table. And then I'll just make one final note. One of the reasons this is valuable or interesting is that having an explicit formula, an analytical formula for calculating a value where you don't need to rely on a table, is that you can generate these terms sort of on their own, but also you can derive other expressions. For example, you can take partial derivatives of the critical t-value with respect to its arguments. You can express the critical t-value now as a function of its arguments. You can look at gradients. You can, for example, bound errors or propagate errors and propagate uncertainty through formula in which this critical t-value arises. There are lots of uses and lots of interesting connections. I didn't go through those here. I just want to be efficient and just sort of show this is the method. This is a method you can use. You can follow everything on the page and calculate analytically without resorting to something like Monte Carlo or gradient descent, some algorithm of that type, to get an explicit form of to any amount of precision you want in terms of a infinite series, and that this computation is actually efficient. All right, so hopefully I got it all out there. Anyway, thanks for watching this video. If you're lost about what I'm saying, I would recommend checking out my previous videos, which really laid the groundwork for where this computation comes from, some reasons for why it may be interesting, important, necessary, and really deep dives into where this comes from, and hopefully will serve as a good foundation for understanding the value of what I've presented here in this video. Okay, thank you.